Hello, and welcome to the latest installment in the Power Systems Design webinar series, Driving the Software-Defined Vehicle, Zonal Architecture, Ethernet, and Internet Power Distribution, sponsored by onsemi. I'm Steve Paul with Power Systems Design. I'm your moderator today. We have just a few announcements before we begin. This webinar is designed to be interactive between you and our presenter, and later in the program, we'll ask for your feedback. We strongly encourage participation and are happy to take your questions and comments. You can participate in our Q&A session by asking questions at any time. Just type them into the Ask a Question text box on the bottom of our console. We'll answer as many questions as time permits after the presentation. Slides will advance automatically throughout the event. And at this time, we recommend you disable your pop-up blockers. If you're experiencing any technical problems, please visit our webinar help guide by clicking on the help ? Icon on the bottom right of our console. And if slides are not advancing, please press the F5 key on your keyboard to refresh your browser. And now on to our presentation, Driving the Software-Defined Vehicle, Zonal Architecture, Ethernet, and Intelligent Power Distribution. Discussing today's topic will be Alessandro Maggini, Regional Marketing Management with onsemi. I'd like to introduce Alessandro. Hello.
Hi, Steve. Thanks. So I will share my screen, if you don't mind. And I hope you are able to see my screen. So good day, everyone, and thank you for being here. So my name is Alessandro Maggioni, so I'm Regional Marketing Director from AMG Europe, so Analog Mixed Signal Group. And today I want to talk about what's really driving the software-defined vehicle. So over the next around 45 minutes, we will look at the three foundational shifts working together. So the first one, the move to zonal architecture. The second one is the role of Ethernet as automotive backbone. And third, an intelligent power distribution. Individually, each one is important, but together they are reshaping how vehicles are designed, wired, and updated for their entire lifetime. Let's say, my goal today is to show you how these pieces are connected, so why they matters for cost, weight, scalability, and safety, and where the industry is heading over the next several years. So I also point out exactly where onsemi silicon fits into each layer, because that's the thread that ties the whole story together. So let's get started. Here is where we are heading today. So we will start with the development challenges shaping car electronics. So then move into software-defined vehicle architecture and automotive Ethernet that ties it all together. From there, we'll get practical, so some software-defined from lighting using 10-base T1S, so RCP, remote control protocol, and lighting controller. We'll see some example. Then a deep dive on powering sensor and SoC with the right LDOs, tracking, voltage tracking, current limit for SoC. And then we will finish by distributing and monitoring power using smart switches, including RCP control and monitoring of those switches. So by the end, you will see how all of these layers connect into one coherent architecture. So let's dive in. These slides capture just how much car electronics have changed in, let's say, in around 3 decades. So if we were back in the 1990s, a vehicle had very few electronic control units, simple software, or very limited, and a low complexity wiring loop. A light switch wired more or less directly to the headlamps, for example. No? Fast forward to a 2020s plug-in hybrid, and you have over 100 ECUs, each running its own software, a far more complex wiring loom, and the same light switch now is talking through a dedicated lighting ECU. No? So, and on top of all that, so we are now meeting stringent functional safety and cybersecurity requirements that simply they didn't exist back then. So every added feature brought another control unit, more wiring, and more software to validate and to secure the overall system. So this relentless growth in complexity is exactly what pushing the industry toward the software-defined vehicle, and sets up every challenge we are discussing next. So today, vehicle electronic face, as we have mentioned before, three core challenges driving the needs for architectural change. First is the wiring complexity. And high-end vehicles carry up to around 70 kilograms or 150 pounds of wiring harness with enormous tooling capex and high manufacturing cost. Second is the software complexity. Today we are, let's say, over 100 ECUs from different manufacturers. So each with its own software approach, means configuration control, cybersecurity are increasingly difficult to manage. And third is the limitation of classical fuse boxes. There's no diagnostic, no ability to power cycle a fade load. There's no way to reserve power for, let's say, safety critical system, just like brakes and steering. Each of these add cost, weight, risk, and none of them scale as vehicle add more features. So these pain points are exactly what Zonal architecture and onsemi's power solution are designed to solve. And let's say we will walk through each one in turn. So how do we tackle wiring complexity? The answer is zonal architecture. Okay, so instead of routing individual power and signal connection to over 100 ECU, which are scattered through the vehicle, so we divide car into 4 or 5 or even more zones, depends on the car. So each managed by its own central computer. Communication within each zone runs on high-speed automotive Ethernet, general 100 megabits up to 1 gigabit per second. And is going to replacing the massive bundles of control wire we've seen today. So each zone also gets its own dedicated power connection instead of feeding over 100 ECU individually, so which dramatically cuts wire length and overall vehicle weight. So now, here's where it gets even more compelling. No? So by moving, for example, from 12 volt to 48 volt as a power distribution voltage, we get 4 times the voltage at a quarter of the current of the same power. So this is a simple electrotechnical physics. So that let us use 50% thinner copper wire, just 25% of the cross-sectional area, so which translates to a 75% reduction in copper weight, which also means copper cost and cable losses. So, and thinner wire also bends more easily. So it can we can route it twice as tightly around corners and through tight space. So also from, let's say, a design perspective of the vehicle itself. So think about what that means at scale for an OEM producing millions of vehicles. No? And there is as a bonus. So changing the voltage let us also redesign the whole system from the ground up. For example, removing legacy constraint like cranking, reverse battery condition. So this is really where onsemi solution create real and measurable value. So let's look at why the classical fuses box is reaching its limit. So most cars today rely on around 150 fuses, more or less. I mean, depends on the car. And high-end vehicles can have 3 separate fuses boxes. So the problem is what they can't do. So there is no voltage of current monitoring. There is no idle mode control. And once a fuse blows after a fault, there's no automatic recovery. So you're literally sending someone out with a spare fuse. The electronic fuse box built on smart switches change all of that. It let us turn ECU off and on and actively manage power for safety critical systems like brakes and steering. It protects against many more fault types and recovers automatically wherever it's safe to do so. The current monitor it provides is essential for hands-off automated driving, where the system has to know exactly what every load is doing in real time. And because it can sense and switch intelligently, it dramatically reduces consumption when the car is in standby, so preserving the battery charge. So Here, for example, you can see in the picture the 2023 BMW i5 rear fuse boxes. Here is a real-world example. So we're also seeing some of those fuses migrate directly into the zonal controllers, which is exactly the architectural direction we expect next. So the software-defined vehicle concept is the other major enabler for zonal architecture. So the idea is quite straightforward. We need to consolidate all application software into a small number of central compute units, removing the needs for application code in each individual ECU. So what means? So this means car features are defined at software level, so which enable over-the-air updates and post-sales customization, for example, and it reduces or removes the need of microcontrollers at the edge. So the central computers communicate directly with load and sensor over the network. Specifically, they use a remote control protocol, or what we call RCP, sending message over Ethernet to a specific dedicated chip. So the RCP chip then controls the loads and sends information about those loads and sensor back to the central computer. So intelligence moves to the center while the edge becomes simple, low cost, and software controller. So this is exactly where onsemi 10BASE-T1S and especially on the RCP solution fits in, and is the foundation of everything that follows. Here in this slide, we see the big picture of what zonal architectures looks like in practice. So as you can see, zonal controls module replaced the traditional central fuse boxes entirely. Each zone in the vehicle gets its own intelligent module that handles local power distribution, diagnostic, and load management. So right next to the load it serves. What's the key here is the splitting between what's decentralized and what stays centralized. So power distribution move out of the zone, closer to the actual loads, but the processing and the decision-making still centralized in high-performance computing. So this gives you the best of both worlds. So let's say shortest wire and fast response times at the edge, while with unified intelligence at the core. So the benefit for OEMs and tier ones are tangible and measurable. So reduce wiring weight, faster diagnostic, smart power management, and improve functional safety, which is also quite critical. And critically, this architecture creates a clear path towards software-defined vehicles, which much easier scalability across model lines and also trims levels. So this is where onsemi fits in. So we provide the key silicon building blocks that make this architecture work. So 10BASE-T1S connectivity for the communication backbone, electronic fuses, and smart switch solution for power and intelligent power management, IC for a clean monitor rails. All of it's designed to work together seamlessly in a zonal system from the backbone down to the individual nodes. So let me show how in piece are connected. So in this slide, this is our starting point for automotive Ethernet. So the simple point-to-point connection. So in this first concept, each device links directly to another over its own dedicated Ethernet link. It's easy to understand it. It delivers the high bandwidth and low latency that modern sensor and processors demands, and it gives you reliability, deterministic communication between two endpoints. But notice the trade-off as you scale. So every new connection needs its own dedicated link, so which means more cabling, more weight, more connectors, and more cost as the number of devices grow. So in a vehicle with dozens of nodes, that becomes quickly unmanageable and undoes the very weight saving we are chasing. Okay, so that tension between performance and scalability is exactly what motivates the multi-drop switches and zonal topology will build up over the next few slides. So think of this as the foundation will evolve from as architecture matures. Now, let's look at how 10BASE-T1S multi-drop Ethernet simplifies the system. Okay, so this is the backbone of zonal architecture, and onsemi offers a complete portfolio with 4 levels of integration. So you can match the solution that you exactly need. So starting from the top, so the MEC plus PHY is our most integrated option. So a full Ethernet stack on a single chip, controller through a simple SPI interface. So that's ideal when when your microcontroller doesn't have built-in MEC hardware. Next, the standalone PHY. This is for MCUs that already have a MEC on board, connected through a standard MI interfaces. Then the PMD, so our most minimal option for MCUs with both MEC and digital PHY built in. Just a 3-pin connection, so with an extremely small footprint and the lower cost. Finally, and this is the game changer, is the RCP interfaces. So here the central controller can directly manage external I/O and peripherals like SPI, eliminated the need for a local MCU at the node entirely. So that's a major reduction in cost, board space, and software complexity at every edge node. Whatever your architecture requires, and wherever you are on the integration course, onsemi has the right level to match it. So that's our 10-base T1S roadmaps, cover every integration point in a zonal system. So with solution for any use cases. So it starts with NCV7311, so our first generation 802.3 CG physical layer, so featuring enhanced noise immunity and EMC robustness. Next is the T30HM1TS2500, so which is a MEC PHY, which is our second generation flagship with a next generation feature, including PLCA, sleep and wake, precision time stamping, harness defect detection, and 48-volt battery support already. So for systems that don't need a local MCU, the new RCP device coming soon will provide directly remote control with a fully open protocol, PTP support, rich GPIO, PWM, and ADC, and backward and forward compatibility across layer 2 and layer 3. And then also the upcoming PMD devices offer a minimal 3-pin analog front-end footprint with topology discovery and sleep and awake. All these are built on onsemi Trio platform, which is a clear path toward monolithic 10-base T1S integration directly into an ASSP. So the 7311 and 2500 are already available now with the RCP and the PMD sampling already. Now, a little bit into the device. So the T302500 is our Open Alliance standard MEC PHY and the most feature-rich 10-base T1S device on the market. So it's the first product to implement both coordinator redundancy and harness defect detection. Two capabilities critical for automotive reliability. Coordination redundancy improve overall system reliability, while harness defect detection, it defines an open, a short, or any missing extra termination on the bus. So additional features included the TC10 compliant sleep and wake, the TC14 topology discovery, GPTP version 2 timestamping, a signal quality index that measures received signal quality, and PLCA diagnostic for detecting misconfiguration. So the device already supports 48-volt power nets and is currently in ACQ 100 qualification. So target application here includes zonal controllers, automotive lighting across front, rear, body style, and whatever interior. It comes in a compact QFN 20-pin 4x4mm package with, of course, wettable flanks, capable for optical inspection. So, of course, the datasheet is released and sample and production are fully available now. So now let's introduce our RCP device and arguably the most disruptive product in products in the 10-base T1S portfolio. So this is designed for edge nodes that need full network connectivity, but don't need should not need a local microcontroller. So that's a fundamental shift in how your architect in a vehicle network. So the protocol is a protobuf based, so and is being standardized through the Open Alliance, and the device is fully compliant with all the key specifications. Sleep and wake up, topology discovery, EMC, timestamping, PLCA diagnostic, and also harness defect detection. So you get the full feature set out of the box. On the power side, it's a PODL, power over data line capable, and handles a battery voltage up to 48 volts. So it's really for the next generation power architecture. So you also get all of our differentiated features, SPI, SPI Plus, enhanced noise immunity, and the GPTP version 2 precision timing with synchronization messages. So flexible VIO pin lets its interface directly with the 3.3 or 2.4 volt devices. And it can also run from a single 3.3 volt supply. So the transmitter is optimized for capacitive coupling to UTP cables, and the MDI pins are protected to plus or minus 6 kilovolt VSD. So with grade 1 ACQ100 thermal protection. So here, if we look at the application diagram and on the right, so the RCP mode connects directly to SPI peripherals like LED drivers or door module drivers, so with no microcontrollers in the between. So the center compute control everything remotely over Ethernet. So that's fewer components, lower cost, and simple bill of materials at every node. So the device is sampling now, and so if it fits your architecture, let's get started with your evaluation. So far, we focus on the connectivity as the backbone of the software-defined vehicle. So this is where the story that comes together. On top of the connectivity, our Generation Plus front LED lighting gate driver family is the driver that completes the offer. It covers the multi-channel front headline with boost, buck, and combination option, delivering high overall efficiency with a minimum external component, high operating frequencies that shrink the inductor, and low EMC emission, so for switching and dimming. So the boost channel drive external interleave MOSFET with external current sensing, while the buck channels are synchronous with average LED current regulation up to 1.6 amp, so of constant current, and also programmable frequency. Crucially, the 4 MHz SPI interface gives software dynamic. It gets real-time control over the lighting, and it proven a software-defined vehicle concept designed for ASIL-B safety goals. So it's, of course, is ACQ100 qualified, and the family spans through the NCV 78902, the 78964, and the 78925. So across the SSOP package. So in other words, alongside the network we have described, so this fully complete the picture. No? So the intelligent software programmable, controllable edge device that brings the architecture to real life. Make an example. So these modules we are seeing these slides brings everything we discussed into one real working board. So is the smallest 11 channel from lighting module we ever built, fitting onto a compact 6x8 centimeter, is a 6-layer PCB, just 48 square centimeters, that's both thermally and MCE optimized. So at its heart is the NCV 78964, which is a buck boost LED driver, paired with 3 78935 buck drivers. So all topside cooled, with the 7895 available as a different assembly option. Together, they deliver 11 flexible output channels, scalable from, let's say, up to from 8 to 11, with 150 watts of maximum power. So what makes it a true software-defined vehicle building block is the RCP approach. So it connects over 10BASE-T1S Ethernet and runs MCUs-less in a zonal architecture. So we viewed over CAN for the matrix manager, and lean driving an external stepper motor for headlights level. Let's say because RCP replaced the microcontroller, there's no software stack on the board, so it's much smaller. It's a lower cost and far simple than a traditional design. On the integration side, it adds two low side bypass switches and high fan switches, a true battery line disconnector, a 5-volt supply, and a 16 ADC input for voltage monitoring, as well LED temperature and binning. So that's onboard EEPROM, that configuration and identification data, and the 10BASE-T1S inputs feed the RCP device directly. So integrated current sensing enable a shunt-less solution for both the boost and the buck stages, so which will further reduce size and cost by removing also an external sense component. In short, so this is connectivity, control, and power working together at the edge. So the whole architecture proven on a single board. So we covered the standard Open Alliance feature, like the topology discovery, sleep and wake up, and PLC diagnostics. So, but what really set onsemi apart are the differentiated feature we built on top. So let me walk through them. So for precision time protocol. So full GPTP2 version 2, support by the 8201 AS for time synchronization and precise event management across the network. So this is essential for coordinating event precisely across zones, especially, for example, in a safety critical application. Second is the PLCA coordination redundancy. So this is a pattern onsemi feature. If the PLC coordinator either fails, a backup node automatically takes over. So the network never falls back to a CSMA CD mode. So this means you keep the full bandwidth and deterministic latency at all time. So adding an extra layer of network protection. Third, SQI Plus. So our enhanced signal quality indicator. So the specification and the standard define 8 levels. So we provide 32, 4 times the precision that spec requires. For detecting cable degradation and network issues in the real time before they becomes a real failure. No? So fourth, the harness defect detection. These are diagnostic potential wiring problems proactively. So think of it as a predictive maintenance for your vehicle network. And fifth, the enhanced noise immunity, which maintain the signal integrity at extremely high noise level, so which directly extend effectively cable reach. So each of these features at measurable system level value, better reliability, longer reach and proactive diagnostic, and none of them are available from any other suppliers today. A little bit more in detail. So PLCA coordination redundancy. This is a patent onsemi innovation that adds a critical layer of network resiliences. So in a standard PLCA network, if the coordinator node fails, so the entire system, the entire segment falls back to CMA CD mode. So you lose the deterministic latency. So the bandwidth drops and noise immunity degrades. So our solution designates one node as a redundant coordinator for continuously monitoring the network, checking that the coordinator sends its beacon at exactly the right time. No? So if it detects a missing beacon, the redundant coordinator automatically takes over the coordination role and starts sending a beacon itself. If the original coordinator returns, so the backup detects and step back to standby in less than 5 microseconds. So this is ensuring there's never more than one active beacon in all the network. Okay, so multiple nodes can even be configured as backup in a full recurrical method, so for extra resilience. So, and critically, while it's an onsemi feature, it's fully interoperable with all the other vendors, transceivers. Okay, so it's a full drop-in into any compliant network without compatibility concern. Harness defect detection, or HDD, so is a diagnostic capability that detects both obvious and latent wiring defects before they impact the signal integrity. It can identify an open on one or both boost wires, or a missing termination, a short between the two boost wires, or extra termination, for example, and a short of one bus wire to the ground or to the supply line. So the diagnostic run in a dedicated mode, controlled by the local management entirely over MDIO or SPI. So one node performs the measurements while all the other nodes stay completely silent. So the entire process takes only about 200 milliseconds, which makes it practically to run on the production line during a service appointment or automatically at vehicle shutdown. No? So onsemi was the first to implement HDD, and it's available in both our Mac5 and LCD products. So this kind of proactive fast diagnostic is exactly what needed for functional safety compliance and for keeping a vehicle network healthy across its whole life. Signal quality indicator, or SQI. So it provides a real-time monitoring of signal integrity across your base T1S network. Any node on the segment can measure the noise of the segment by monitoring increases in the bit error rate. So with SQI calculated as a signal to noise level ratio. The standard Open Alliance specification defines 8 levels, from 0, meaning no links, up to 7 for the best signal. onsemi SQI Plus implementation goes significantly further, so with 32 levels of precision, so giving 4 times the granularity for detecting subtle degradation. No? So that extra resolution basically lets you assess the network layout error, aging, wrong termination, and for example, faulty or degraded cables and components. No? All in real time without taking the network completely offline. So instead of waiting for a hard failure, engineering teams can get the data they need to predict problems before they happen and to maintain network reliability over the vehicle's entire lifetime. So effectively turns the network itself into a continuous health sensor. Precision Time Protocol, or PTP. So there is an implementation that delivers best-in-class time synchronization supporting the GPTP version 2 by the 802.1 AES protocol. So we achieve less than 100 nanoseconds, total worst case time difference between the grandmaster clock and any follower node on the network. So with 8 nanoseconds granularity, so you can set the precise time of any action. So the system can even support out of order scheduling of timed operation to achieve the maximum flexibility. So here's how it works. So an internal PTP timer exchanges time-stamped messages between devices to establish a common time reference, and a PID loop compares timestamps across the network and performs any necessary compensation. So a key differentiation is that our timestamping happens directly into the physical layer. So the host microcontroller doesn't need to implement a timestamping interface itself. So this matters for asynchronized lighting sequences, for example, coordinated sensor sampling, and any function required tight temporal alignment across any zonal boundaries. No? So PTP is built into both the MAC-PHY and the new RCP devices, which show already in the previous slide. Now, let's go inside the zonal control and look at one of its most critical building blocks, so the LDOs, or load dropout regulator, as we want to call it. So as we consolidate the function into zonal controllers, those controllers have to cleanly and effectively power a wide range of sensor and high-performance SoCs. So each with its own voltage, noise, and accuracy requirement. That's exactly the job of LDOs. So in this deep dive, we will work through the different types that matter here: tracking LDOs for remote sensor, current limit LDOs for rugged protect rails, and LDO designed specifically for SoC and image sensors. So the goal is to show why the right regulator choice directly affect the power efficiency, also the thermal behaviors, the signal quality, and also the reliability of the whole zonal architecture. No? So get it wrong and you pay for it in heat, noise, and videos, basically. So get it right and the system just works. And so let's take a closer look at what each of those devices bring into the table. Let's start with our tracking LDOs family. So designed specifically for powering remote sensors in automotive application. These regulators span 50 to 30 milliamps and are built to survive the real automotive environments with a wide operating range from, let's say, minus 40 up to plus 45 volts, and handle transients like load dump and cold crank. So what really sets them apart is the precision. So a tight output tolerance, or just plus or minus 40 millivolts, with a very excellent linear load regulation around half a millivolt. So your sensory measurements stay accurate under varying all the battery conditions. So these include integrated protection, so reverse polarity, reverse current, short to ground, short to battery, and so on, with a reverse current leakage of just 0.1 microamps maximum, and 1 microsecond maximum fault response time for safe. This helps to have a very reliable design and safe design. So load dropout keeps them efficient and reduce all the self-heating. And you will find them across traction inverter, zonal controller, instrumental cluster, central display, braking, steering, and all the battery management systems. So the lineup ranges from 70 to 30 milliamps in a standard SO8 or SO8 with exposed path, depending on the power. And we are starting to sampling for Q3 of this year, with the production expecting Q2 for the next year. Next is our adjustable current limit LDO family. So this is built for the demanding loads in the zonal architecture, rated up to 150 degrees operating junction temperature. So those are rugged parts with maximum input voltage up to 48 volts and up to 70 or even 90 volt absolute maximum with the 8737 or the 8740, with full protection for the 12 volt power net and the reverse voltage protection down to minus 42 volts. So the standout feature is the adjustable current limit. So you can simply set it with a resistor connected to the CO pin. So a single device covers many use cases. So this also offers an adjustable output from, let's say, to 5 up to 20 volt, with fixed voltage up to 3.3 and 5 volt option. So ultra low, 5 microamps quiescent current, accuracy down to 1% at room temperature, and a power good flag with a programmable delay, all stable with just only 1 microfarad of ceramic capacitance. So that combination makes them ideal for power-hungry compute unit, traction inverter, ADAS, in-vehicle infotainments, head-up display, and so on. Next is our T30L bias LDO. So it's a 1 amp, 3.3 volt devices purpose built to power the SoC and image sensor, and is at the heart of the zonal architecture. So, and what makes it special is that it's built on our Treo platform. So the Treo foundation is exactly what delivers the benefit you see here. Because Treo uses an advanced high-precision CMOS process, we can hit ultra-low noise of just 7.5 microvolts RMS and a very high PSSR, so which means clean, stable power for the most noise-sensitive imaging and compute rates. Treo precision also gives us plus or minus 1% output accuracy across load and temperature, with very ultra-low power of around 25 millivolts at low input voltage. So design run cooler and more efficient. So the bias rail range cover from 2.5 to 3.3 volts and a 1.2 volt logic level make it compatible with a wide variety of power sources without level shift. So just importantly, so the Treo platform is scalable and configurable. So we can offer other voltage options on request and adapt quickly to a customer with exact rate. So it targets zonal controller, automotive display, high performance computing, and is available today in a compact WCSP 6-pin package and QFN package with wettable plate. So we are sampling now in CSP. We're sampling in DFN in Q4 of this year. So in short, the Treo platform is what turns this into a precision, future-ready building blocks for software-defined vehicle. Now, let me introduce the T30-165. So this is a 30 milliamps low dropout regulator with a 3.3 volt maximum input and an ultra-fast dynamic response to changes in load. What sets it apart is the market-leading transient performance. So he's able to handle a 0 to 30 for 300 milliamp step in only 100 nanoseconds. So all the voltages undershoot to just 37 millivolts and settling with only 1 microsecond. So the point of load rail stays tight even under sudden demand. That's a real advantage for image sensor and processor that switch states very quickly. On top of that, an ultra low dropout of just 26 millivolts, so the full load, keeps efficiency high and heat generation very low. So, and the part remains stable with just also 1 microfarad of effective output capacity. So, which helps also to shrink the overall solution size. It holds output accuracy to within plus or minus 1% across full loads and temperature. These are really ideal for precision-sensitive rails. And also in this case, also the 1.2 voltage level enable connected die to modern processor and reduce the level for any level shifting circuit. Also in this case, we have samples for the CSP 4-pin package. And the TFNN package option is going to be ready for sample in the fourth quarter of next year. So this slide pulls the power story together into a complete architecture. So instead of one big traditional fuse boxes, the zonal control module combined with centralized power distribution now cover all those fuse boxes functions. So distribute intelligently around the full vehicle. So the key point I want to land here is that is enabled by our Treo platform, because the smart switches and the power distribution devices in the zonal module are built on mostly on Treo. So we get tightly integrated current and voltage monitoring right where the power is delivered, which is exactly what software-defined power management and hands-off automated driving demand. So Treo high precision mixed signal process means sensing, protection and control all sit in a single scalable platform. So the result is less wiring, lower weight, real-time diagnostic, automatic recover, and lower standby consumption. So all governed by a software and updated over the air. So this is the power backbone for the rest of the section which are building on. So let me introduce our new smart power family, which is now full in production. So the NCV84003F and G are shipping today. with the full lineup rolling out through the rest of the year. So the family covers standard high-side switcher and eFuse direct-to-drive products with RDS-on ranging from 2.3 million to 16 million to a single platform, which is able to address everything from zone controller channel down to body, lighting loads, and so on. So 4 key differentiators are set apart. So first is that the entire lineup is rated to ASIL-D, which shortens your safety qualification effort. Second, tighter transient response, which is improving system safety during fault and switching events. Third, automatically entry and exit of capacitive charge, which eliminates the needs for a dedicated GPIO and a firmware logic to manage this inrush current. And fourth, a more flexible resistor-based I2T implementation, which provide continuous protection adjustment instead of a fixed step. So you can precisely match each load profile. On top of that, every variant is hardware and software drop-in, pin-to-pin replacement with already incumbent parts. So enabling dual sources supply, resiliency with basically zero redesign. So board and sample are fully available. So we'll say better protection, simple design, ASIL-B out of the box, and available today. The NCV84OXXF SmartFET is our 12-volt fully protected high-side driver. So a little bit more in detail here. It's a family with advanced diagnostic. Keep providing low protection up to, let's say, 20 amps nominal and up to 120 amps transient. So it targets zone controller, power distribution units, fuse replacement, body electronics, lighting, ADAS, domain controller, and so on. So the key differentiation includes fault differentiation on the current sense output. That's for a faster fault detection. So isolation and also resolution. Intelligent retry during in-rush that limits current overshoot to protect all the downstream load. And differential thermal shutdown that enable early failure detection than a conventional approach. So the entire family is developed to ASIL-B in compliance with the standard ISO 26262 with a complete safety package fully available. And it adds thermal shutdown, reverse battery, over voltage, under voltage, loss to ground, DCC, and also ESD protection. So quiescent current is only 500 nanoamps maximum for a minimal power consumption. And it comes in a standard compact TCSOP14 exposure pad with a standard, let's say, package on the market. If we look at the F family, so this is our 12-volt fully protected high-side drive family targeting zone control and let's say eFuse. So this is basically I2T capability. So this is basically a refuse is able to, let's say, 3 features released apart. So current sense pin and adjustable, let's say, I2T, not able to anymore with steps, but with 2 resistors, which are able to fine tuning and increase the granularity of each session and of each, let's say, project. So here's the full NCV84OXX family schedule, spanning both the F series SmartFET and the G series SmartGuard variants. So all products come in the same compact TCSOP14 exposure package, so which is S4.9 by 3.9 millimeter. So they are mechanically interchangeable across the lineup. The family range from low resistance, 2.3, let's say, million, single channel up to 16 million parts with a dual channel option of 8 and 12 million. So sample and evaluation boards are available now across the full single channel lineup with a dual channel sample following suit. So the market release timing is aligned for production readiness in the 2026. So whatever you need, a low resistance path for high current loads or a higher resistance if used for smaller load. So this family as you cover with a single pin-to-pin compatibility for each channel. So here we go a level deeper into our RCP circuit controls and monitors such as smart switch in a fully digital only configuration. So just an example. So on the control side, the RCP provided 2 output, so switch 1 and switch enable 1. So this activated the switch and the reset fault condition. So the system can turn power on, off, and recover without any software in the loop. On the monitoring side, we have 2 inputs, so the CS1 and the CS2. So each compare against external reference voltage. So CS1 goes high at 80% of nominal loads, and that's a clearer path. So it's an early warning of a possible overload, so the system can back off power before anything actually trips and recover gracefully with, so dramatically improves fault tolerances. CS2 and then flex at a lower error warning level, so give you a second threshold to act on. So the real advantage of doing this directly, rather than, for example, lower over an SPI bus, is the speed. So direct current sensing reacts far faster than SPI-based sensing. So because you are not waiting on bus transaction or point. So in a safety-critical software-defined power network, where you may need to protect brakes or steering in microseconds, so that response time is exactly what you need. So this is a simple, faster tier of smart switch control, and this set up the ADC-based approach we will look at next. Here, so building on a digital-only approach we just saw, so this is the same smart switch control and monitoring, but now with analog to digital converter in the picture. So the RCP protocol supports ADCs, so today either through SPI or directly controlling the register. So adding that ADC greatly extend our fault tolerance capability. Because we move from simple threshold flags to actual measured values. No? With it, so the central compute software can now data log voltage and current continuously across all the smart switches in the vehicle. That opens the door to generally predicted behaviors. No? So the system can spoil early warning signs of out of normal operation, even when parameters is still technically within its operating specification. No? And then the central compute unit can take early remedial action before it even becomes a fault. And if we also sense the battery voltage, so we can monitor each switch's VDS by calculation. So giving us even deeper visibility into the health of the power. So between the digital only mode, this ADC-based mode, you can dial in exactly the level of monitoring each load. So this is really where smart switches becomes full participant in a software-defined self-monitoring power network, and not just a protection device, but really sensor feeding the central intelligence. So as conclusion, so if to bring this all together, so let's contrast where we were with where we are heading. So back around 2020s, a typical plug-in hybrid carries over 100 electronic control units. So each running its own software, all bound together by highly complex wiring loop. Every function was point-to-point, flip a light switch and it talks directly to lighting SUs. It works, but it didn't scale, okay? So it carried enormous weight and cost, and crucially, it offered no real path to automated driving. So now look at the models we expected for 2028 and beyond. Instead of scattered SUs, we moved to just 3 to 5 zones, including door zones plus a central compute unit, I would say. The lights are controlled from a front zone. The wiring becomes modularized in 48-volt looms, and intelligence shift to the center. So, which the whole vehicle controlled from the central compute. This is the software-defined vehicle. So, function-defined software, updated over the air, with far more support for automotive driving. The takeaway is simple. We are trading complexity and age for intelligence at the core. That means lower weight, lower cost, easier upgrade, and real foundation for safety and cybersecurity as car becomes more autonomous. No? And across every layer we've discussed, so basically connectivity, lighting, power, and sensing, onsemi as the silicon building blocks to make it happen. So the question mark in the middle is the opportunity and exactly where the industry is investing. So thank you. So that was the last slide. So I would also like to show here the contributor for this presentation. And then if you have any question, just let me know.
Okay, well, Alessandro, that was an excellent presentation. Welcome to join me for a couple of questions from our audience. And thank you very much. I want to remind our audience that you can also download a couple of resource documents on our console. So we've got a few minutes here, and we do have a number of questions. So let's get started here. I have one from Well, Goran, who wants to know, do you think that OATC18 RCP will be a booster for deployment of 10 base TIS in automotive?
That's yep, definitely a good question. Yes, we definitely see that because that is the most disruptive in this integration. Because as we saw in the presentation, so is moving the let's say the sensor to the edge and remove the microcontroller from the edge, but put in centralized. So this will help to have a more scalable and also let's say more costless solution because we are removing the local MCU, keeping more simple the overall system.
I see. Okay, thank you. Question here from Dennis. How does zonal architecture physically reduce wiring, and why is 48 volt central to it?
Yes, so basically, we saw the beginning of the presentation. So instead of a point-to-point wiring up to more than 100 ECUs, even more, so the vehicle is partitioned into 4, 5, slightly more zones. So each with, let's say, a local controller and a single power feed. So let's say interconnected by automotive Ethernet. I mean, let's say the high-speed band. Okay, so moving the distribution rail from 12 volt to 48 volt, delivering the same power, but with, let's say, 1/4 of the car. So the conductors really can shrink 25% cross-sectional area. So this means 50% thinner copper and cutting the weight, the cost, and also the I-square resistance cable losses more than around 75%. So while the thinner gauge also able to bend, so those helps to have a better, let's say, design of the system itself.
Very good. What does RCP actually replace at an edge node, and how does the control path work?
Okay, so this is similar to the previous let's say, question. Let's say the remote control protocol, or RCP, removes all the local microcontroller and its software stack from the node entire. Okay, so the central compute with issues these protobuf based messages over the 10 base T1S Ethernet to an RCP device. So, which then drives local peripherals over the SPI. An LED driver, can be a door modules, driver, or whatever. No? And then stream sensor load telemetry back. So, for example, we saw the example of the 11 channel from lighting module. No, that's for example demonstrate how it works. So, it's a MCU-less, it's a shunt-less board. So, where the 10 base T1S input fits the RCP device directly. So, it has an EEPROM on board for full configuration. So, which is the result. So, why it needs. So, basically, you have a fewer components. You have no nodes level software and reduce bill of materials and the size of the board area.
Okay, thank you. Graham wants to know, how do the network diagnostics, HDD and SQI plus, work at a signal level?
So basically, the harness defect detection runs in a designated diagnostic mode where one node measures while all the others stay silent. So there's a controller, we have SPR or MDO. So it detects open and one or both bus wires, so mixing extra termination, so and so on. So that helps in about 200 milliseconds. So that's fast enough for product line service or startup. So on top of the SQI, continuously measurement segment signal to noise by monitoring the single bit error rate. So resolving 32 levels versus only the specification, which is only 8, so which means 4 times more the granularity. So you can flag aging, wrong termination, and the degraded cables before you have a heart failure. So effortlessly turning this into a continuous health sensor. So working together, the two features are really improving the safety of the overall system.
Very good. We have time for a quick couple more here. So why do LDO choices matter inside the zonal controller, and what specs stand out?
So yes, so why LDOs are important in this regard? Let's say zonal architecture must clearly power several sensors, okay, and high performance, for example, SoC. So so each of those with a distinctive voltage, different noise, and different accuracy. Okay, so regulator choice directly also drive the thermal behavior, drive the signal quality, and also the reliability of the overall system. If we take, for example, the tracking LDO family, which operates to a very wide input voltage range, survives all of the low dumps and all the cold crank transient. So with a very, very tight output tolerance. No, this is fitting, for example, accurate remote sensor measurement. So it integrates also, for example, all the RPP, so RCP. We talk about S2G and all the protection, and also together with a very, very low current, reverse current leakage. So we're talking about less than 1 microamps in a very fast response, so only less than 1 microsecond. Also, we need to take into consideration the live load regulation, no? So which is in this case only, let's say, to 0.5, 0.6 millivolt for what is line load. No? So this is also important because also the load dropout keeping the self-heating down across braking, steering, BMS, and instrument cluster rails. So it's really helped to have a full healthy system and compact.
Okay, and quickly, let's squeeze in one more here. What makes PLCA coordinator redundancy important, and how fast is the failover?
Yeah, this is a great question. So in a standard PLCA network, so as we saw in the slide, so basically, if you're losing the coordinator, which is one that sending the beacon, to set up all the system, the specification, if the coordinator loses the beacon, so basically there's a fallback to CMA CD mode, so which is sacrifice the deterministic latency, the full bandwidth, and also increase reduce the noise immunity. So our patented redundancy designates a backup node that monitors the coordinator's backward timing. If on a missing beacon is there, so it assumes the coordinator roll automatically, and when the original returns, it steps back to standby in less than 5 microseconds. So this is guaranteeing never more than 1 active beacon. So on top of, for increased safety, you can multiple backups can be configured in a hierarchical way, and the feature is completely interoperable with all other vendors transceivers. So today we have the 2500, which is the first product which is able to implement it on the market.
Okay, fantastic. And unfortunately, that's all the time we have for today's broadcast. We want to thank everyone for attending today's Power Systems Design webinar, Driving the Software-Defined Vehicle, Zonal Architecture, Ethernet, and Internet Power Distribution. Shortly after this live event, we'll send you an email so you can access this presentation on demand. And on behalf of our guest, Alessandro Maggioni, Regional Marketing Management with onsemi, we want to thank you for your time. And have a great day.
Thanks a lot.